Welcome to The Explainer. Today, we're taking a seriously fascinating journey. We're going to trace the entire life cycle of software. We're starting right at the very beginning, typing code into a terminal, and following that code all the way down to the physical silicon to see how it actually executes inside a CPU core. It's an incredible process, and seeing it visually, well, it really makes the whole thing click.
Here's our roadmap for today. We'll hit the Developer Command Center, version control with Git, team collaboration workflows, inside the CPU, and finally, threads and parallel processing. Let's do this properly, really building one concept logically onto the next.
Starting us off, Section 1, the Developer Command Center.
All right, we've got to start where every single developer, and yeah, even modern AI coding tools starts, the fundamental environment where software is actually built. Now, if you're somewhat new to looking under the hood, the terminal can look incredibly intimidating. It's often just this dark, blank screen with plain text flashing right back at you. But honestly, it's simply your command center. Instead of clicking icons or menus with a mouse, you're talking to your computer directly, using written text commands. Whether you're using a modern editor or an AI coding assistant, the terminal is still absolutely the most direct and powerful way to communicate with your machine. To really grasp how modern applications work once you start building them in that terminal, think of a restaurant. The front end, that's the dining room. It's literally everything the user sees, clicks, and interacts with. You know, the menus, the tables, the ambiance. The back end is the kitchen. It's back there processing data, storing ingredients in a database, completely hidden from the customer. And the API? That's your waiter, taking your request from the dining room, handing it off to the kitchen, and bringing the finished response right back to your table.
So once you write that code for the front end and back end, it's got to get out into the world, right? It actually moves through 3 distinct deployment environments. First, it starts local, running safely just on your own computer where you can experiment totally freely. Then it moves to staging. Think of this as a private testing ground that mimics the real world, so you can catch those annoying bugs before anyone else sees them. And finally, it hits production. Production is the live, real deal, the application your users are actually seeing and interacting with on the internet.
Which brings us to Section 2, version control with Git.
Now, what happens when you make a mistake while building all this, or what if you just need to track your changes over time? Think of Git like a magical resume document. Look, we've all been there, right? Saving files as resume v2, resume final, really this time, it is total chaos and it eats up your storage space. Git basically replaces that mess entirely. Instead of dozens of separate files cluttering up your machine, Git remembers the entire history of a single file for you. You can literally rewind time to any previous version without duplicating a thing. So the real trick here is just mastering this simple 3-step cycle. First, git init tells your computer to start tracking a specific project folder. Then, git add moves your changes into a staging area, kind of like a draft space where you review your work before committing to it. And finally, git commit permanently saves those staged changes to your local history, complete with a message explaining exactly what you did, like fix the login button. Mastering this cycle lets you safely draft and save your code's entire history locally.
All right, moving on to Section 3, team collaboration workflows.
Saving code locally is awesome for a solo project, but how do entire teams of developers build a massive app together without constantly overwriting each other's work? The answer is branches. Branches are essentially alternate timelines, like a multiverse for your code. If you want to build a new feature, you just create a branch off the main code base. You can experiment completely safely in this parallel version without breaking the live app. Once your feature is working perfectly, you just merge that branch right back into the main project.
Teams usually have different strategies for managing these branches, typically choosing between 2 main workflows. You've got Git flow, which is rigid and highly structured with multiple branch types. It's absolutely perfect for enterprise software with strict, scheduled releases, where safety is the #1 priority. On the flip side, there's trunt-based development. This is a minimalist, high-performance approach where developers merge small chunks of code directly to the main branch rapidly, often multiple times a single day. It's all about pure speed and continuous integration.
Okay, so you've written the code, your team has safely merged it, and it's deployed. But how does the actual physical machine sitting on your desk execute those text commands? Let's shift gears a bit and see how this transitions into the physical realm of silicon and microchips. That takes us to Section 4, inside the CPU. We're officially leaving the software world and entering the absolute brain of your computer, the central processing unit. Now, historically, a CPU was just one single processor core. It could literally only focus on one thing at a time. But today's engineers, they figured out how to shrink everything down to a microscopic level. They're packing 4, 8, or even 64 miniature, independent processing cores into a single physical chip.
And this shift, it was a massive computing revolution. Think of a single-core CPU like a heavily congested one-lane road. Every single program just has to wait in line. But a multi-core processor? That's a multi-lane highway. It allows your system to handle all that traffic simultaneously. And that is exactly why you can run Photoshop, stream Spotify, and have like 30 Chrome tabs open at the exact same time without your computer completely freezing up. The workload is just distributed across multiple independent lanes.
Finally, Section 5, Threads and Parallel Processing.
To truly grasp computing performance, we can't just stop at counting physical cores. We have to look at how these individual cores maximize their own internal efficiency, which brings us to threads. If a physical CPU core is a chef working in a kitchen, a thread is basically a second pair of hands for that chef. It doesn't mean you have two distinct chefs, but it lets your one chef chop vegetables while they wait for a sauce to simmer. It's a virtual extension that lets the core juggle two instruction streams instantly, keeping the hardware constantly busy instead of just sitting there waiting around.
Now, there is a very clear difference between clock speed and core count, and honestly, people confuse these two metrics all the time when buying a computer. Clock speed, which is measured in gigahertz, is how fast your chef cooks. Core count is how many chefs you actually have in the kitchen. Both are super important, but they solve entirely different problems when it comes to executing software.
As you can see here, different workloads demand entirely different hardware traits. A gamer, for example, wants a few really fast cores, meaning high clock speed. Why? Because game physics and AI logic have to happen in a strict sequential order. I mean, you can't calculate a bullet hitting a wall until the bullet is actually fired, right? Meanwhile, a 3D animator wants a massive amount of cores to share the heavy lifting, since rendering pixels on a screen can easily be split up across dozens of processors at the exact same time.
So I've got to ask you this. If you go out and drop a ton of money on an incredibly expensive 16-core CPU, does that automatically make all your everyday programs run faster? Well, the surprising answer is often no.
And this right here is the vital connection between everything we've talked about today. Parallel processing only works if the code, the very code we discussed managing back in our Git branches, is actually designed by the developer to be split up. If the software is written sequentially like that one-lane road, your extra 14 processing cores are literally just going to sit idle and take a nap. You're paying for silicon that does absolutely nothing, all because the software doesn't know how to use it.
Which really brings us to the future. As AI begins writing code far faster and infinitely more complex than humans ever could, will the software of tomorrow finally evolve to automatically unlock the massive parallel power of the hardware sitting on our desks? It's a pretty fascinating thought to leave you with. Everything is connected, from that first terminal command you type right down to the multi-lane highway inside the silicon. Thanks for joining me on this explainer, and keep questioning how your digital world is built.